Welcome back, everyone. In this lecture, we're going to talk about the independent samples t-test. This is going to be the first of two types of t-tests we're going to be discussing this semester. Within this lecture, we're going to talk about when to use the independent samples t-test. We're also going to cover the assumptions. Then we're going to walk through a couple hypothesis testing examples. We'll use our first example to paint a large picture of the step-by-step process of the hypothesis testing steps. And then at the end, I'll have two quick ones that you can sort of practice for yourself. That's where we're going to see practice examples 2 and 3. The reading that goes along with this particular lecture is Chapter 6, Module 11 from your 4th edition of your textbook. Next slide. So when do we use an independent samples t-test? Well, as you may recall from our previous lecture, the t-test is an inferential statistics test that we use when we only have access to sample data, and at the crux of it, we're looking to compare two groups. So you're going to see that for all t-tests, you're going to see this underlying notion of comparing two groups. So let's take a look at when to use. So when to use, comparing sample means between, once again, two different groups to see whether or not the populations they represent are significantly different from one another. So once again, we have access to sample data, but we want to use that sample data to make an inference or draw some sort of conclusion about what's going on in the larger population those samples were drawn from. So what are the variable requirements? And this is, I want you to pay really close attention to this variable requirements portion of this slide, because as we go from one inferential test to the next, one of the toughest things that a lot of people have, one of the most difficult things they have is trying to figure out when to use what test. When do I use an F-test, a Z-test, a T-test, regression, chi-square, all that sort of stuff. So as we go through each one of these tests, I'm going to have a breakdown in a slide like this to help you choose, is this the appropriate test to use? So looking at this, we've now separated into both an independent variable and a dependent variable, right? Because a good research question, we want to know, does this thing cause or affect another thing? So the independent variable for the independent samples t-test, first, we can only have one independent variable, one causal variable. And that variable is limited. It's limited to being qualitative or categorical. So remember, that's that nominal or ordinal level of measurement. So it's a categorical variable, and a further restriction is we can only have two categories or two groups within that variable. So for example, if we had gender and we measured it simply with male, female, or if we had political party and we simply were comparing Republicans versus Democrat, or if it was some sort of experimental treatment and we want to say those who received treatment versus those who did not. So it's two groups that are being compared. Moving down to the dependent variable, our outcome, our effect. Once again, we are limited to having only one dependent variable. And for this test, that dependent variable must be quantitative or continuous. Thinking about levels of measurement, that means it's at that interval or ratio level of measurement. So an example, and this is going to be the first example that we're going to see some actual SPSS output for in a couple slides. And we ask sort of a silly question, but something to keep us going. Is there a significant difference in the strength levels between two rival prison gangs? So let's imagine that we want to say, does the prison gang you're in have an impact, or is it associated with your strength level? So you'll notice here I've set up our independent variable, prison gangs, as being a categorical variable with only two groups. Those two groups are the innocents and the meatheads. Then our dependent variable, let's see if it fits the requirement of being quantitative or continuous. We're measuring strength level. Well, how do we measure strength level? We're measuring it by the maximum bench press weight in pounds, right? So if I said, how much can you bench press in pounds? Somebody may only be able to bench press 40 pounds, somebody may be able to bench press 400 pounds or anywhere in between, so it fits that nice quantitative continuous level of measurement. All right, so let's dive in a little bit deeper. Next slide. All right, now as I started off this semester with, when we talked about using parametric tests, one of the things that we have to keep in mind is in order to use them, we have to make sure we're meeting the assumptions of that particular test. So for the independent samples t-test, there are three main assumptions that we want to take a look at, in order to see whether or not our data will actually, meet those assumptions. So the first one says that the dependent variable is normally distributed within the population of each group. So what this is asking is it's saying, well, is the bench press, when we look at the distribution of bench press weights for each one of these groups, does it look like that normal bell-shaped curve? The nice thing is, because we are working with sample data and we learned about the sampling distribution of the mean and something called the central limit theorem, this is not an assumption that is going to be too problematic for us. Typically, people say as long as you have an overall sample size of 25 or 30 or more, you don't have to worry about this because the sampling distribution of the mean takes care of that one. So for at least for the sake of this class, we're not going to worry about assumption number 1 much. So let's move on to the next assumption. Assumption 2, it says that the observations within each group are independent of one another. Well, what does that mean? Well, what it means is that how strong one of the people in the meathead group is should not have an influence on the strength of somebody in the innocence. So in other words, they're independent. A violation of this would be, imagine some of you may go and work out with a workout partner or a friend. Well, sometimes you don't feel like getting out of bed and going and doing your exercise, but your friend calls you or texts you and says, come on, lazy butt, let's go. And that would be something where the two of you are dependent upon each other. You're correlated. How much you work out is correlated with how much your friend or partner works out. For an independent samples t-test, we don't want that. We want you to be working, if you're part of the meatheads, that you work out when you work out. If you're innocent, you work out when you work out. There's no correlation between those two groups. So for the independent samples t-test, this is something that we sort of look at just what do our samples look like? Do we have relatives within the samples? Do we have close friends? For the most part, I'm not going to throw you any curveballs this semester. Usually we don't have to do much. If I say it's an independent samples t-test, you can assume that the independence has been met. If you were to come across in a real life situation something where you violate independence, well, that's going to be our next lecture where we talk about the dependent samples t-test, otherwise known as the paired t-test. So that will be in our next lecture. All right, so assumptions 1 and 2, we don't have to spend a whole lot of time on. Let's move down to the third assumption because this one is extremely important for us statistically to pay attention to. So assumption number 3 is called homogeneity of variances. What the heck does that mean? It means that the amount of variability in the dependent variable is roughly the same between both groups. So how much variability and strength there is for the meathead group needs to be roughly the same amount of variability and strength that we see for the innocence group. So with looking at those ones, how do we measure that? We need to use something called the Levines Test for equality of variances. So homogeneity is just a fancier term for equality. That's it, being equal. So it's so important that when we look at our SPSS output, we're going to see SPSS automatically includes the Levines Test for equality of variances. And that's going to be a very important part of our hypothesis testing. So we're going to see that in more detail in the next few slides. All right, so once again, quick recap for the main assumptions. There's 3 of them, but for the sake of this particular statistics course, the third one, homogeneity of variances, is going to be the one that we need to pay the closest attention to. Let's move on to the next slide. Quick review of hypothesis testing. So as I may have told you a while back, pretty much every test we're going to walk through this semester is going to focus on these 6 steps. You've seen this before. All we have to do is personalize it to the particular test we're working on. We start with a research question. We then translate that into a null and alternative hypothesis, or null and research hypothesis. We have to set our level of alpha. We then look at critical values, the observed value, and then we make our particular decision. Let's go ahead and get started. Next slide. Here is a picture of an SPSS output for an independent samples t-test. And as you can see, let's just take a look at what we're seeing on this particular slide. You'll see that it says results of an independent samples t-test comparing bench press weight in pounds between 2 rival prison gangs. So that first box, the box that's titled Group Statistics, this gives us information about our variables and our sample. So if you did not have that heading at the top of the slide and were simply given this output, you start with the group statistics and you can start to get an idea of what you're looking at. The first thing we see to the farthest left of that box, you'll notice it says maximum bench press in pounds. That is our dependent variable, our outcome. And that was the one that was measured in a continuous fashion. So maximum bench press in pounds, our dependent variable. You move over just a little bit and you see the column, sort of column titled gang. Under gang, you see two different rows. You see innocents and you see meatheads. That right there represents our independent variable, that categorical independent variable with only two groups, the innocents and the meatheads. And then as we move from left to right in that group statistics box, you'll notice there are two rows of information, one for the innocents, one for the meatheads. So we see that the N is the sample size for each of those groups. There were 23 innocents, 27 meatheads. That's just N sample size, nothing too fancy. Then we see the mean. This is where we're really focusing. That mean is their average bench press weights for each group. So by looking at this, it says that the innocents for that group, their average bench press weight was roughly 263 pounds. For the meatheads, their average bench press weight was roughly 283 pounds. So in our sample, it looks like the meatheads are stronger guys, right? I mean, if you look at it, you're like, okay, they're about 20 pounds heavier, 20 pounds stronger than the innocents on average. But that's sample. We want to know, based upon our sample size and the difference between those two group means, is that enough for us to draw a conclusion that if we were to extrapolate this and use this to make an inference about the larger population, would that same finding hold true? And that's the whole point of doing this hypothesis test. So that's the group statistics box. We look down at the bottom box, that's our independent samples test box. That's where we're going to see all the good information that we need for our t-test. And when you look at this, you'll notice there's a lot going on. We're going to break it down in more detail in the next couple slides. But a quick look at that independent samples t-test box, you'll notice as we look at the tops of the columns, there's one area that says Levines Test for equality of variances. This is what I was talking about on the previous slide, where we need to figure out, do we meet that assumption of homogeneity of variances? And if we don't, then we need to have a backup plan. And that's why we have two rows of information in this box. We have an equal variance is assumed row of information, and when equal variance is not assumed. That's going to be one of the pivotal points in doing this test appropriately. Then when you look more towards the right of that box, you'll see that it's overall titled T-Test for Equality of Means. This is where we have all the information that we need. The T-statistics, something called the degrees of freedom, a sig two-tailed, confidence intervals, all that sort of stuff that we're going to want to work with. So as we're going forward, you'll notice on this test, you are not going to actually have to compute or do any calculations to figure out things. Rather, you are going to need to pull the right information from this output and know how to interpret it. So that's kind of the change that we're doing in this course. It's going to be less about doing the actual math by hand, and it's going to be more about, can I understand what I'm seeing on the output? All right, let's go ahead and get started using this hypothesis testing example. Let's move on to the next slide. So our first step in any hypothesis test is the statement of the research question. So as I've mentioned before, and I'll mention again right now, we're asking a question, is there a significant difference in the strength levels between two rival prison gangs? And as you can see on this slide, I've once again replicated that group statistics box that we saw from the output. And we can see here that it appears the meatheads are stronger because their mean level is higher than the innocents. But is that difference enough for us to conclude that this would hold true in the larger population? And that's what we're here to set up. Let's move on to the next slide. In slide 2, we now need to transform our research question from step 1 into two competing statistical hypotheses. So just like we've seen with other tests, we have the null hypothesis, H0, and we have the research or alternative hypothesis, H1. So you'll notice here the way that I've set it up with the null hypothesis is if there's, and remember null always means no difference, no effect, no change, right? So how do I represent that using the various symbols and things that we have? Well, I've got the mu. Remember, mu is what we're trying to estimate. It means the population mean. So I'm saying that the mu for the innocents, and that's why it says mu I just put a little I so you know which group I'm talking about, equals mu for M, the meatheads. If there is no difference in the average maximum bench press weight between the two gangs, then there should be a zero difference between them. And that's why we have it as mu I equals mu M. Our research hypothesis on the other side would say that there is a difference, right? We're not predicting a directional difference. As I've stated before, we are always going to be focusing on two-sided or non-directional tests in this course. So that's why our research hypothesis is simply saying, well, there's either, if there's any difference at all, we need to capture that. So that's why it's set up as mu I does not equal mu M. So if there is any difference at all, that's what that is being reflected to say that there is a difference in the average maximum bench press weight between the two gangs. Let's move on to the next step. You'll notice this slide is rather simple, and that's kind of nice because alpha, at least for this course, we're always going to set alpha at 0.05, period. Not going to change. I'm not going to throw you into curveballs. That's it. So we assume alpha is going to be set at 0.05, and we set it that way. Let's move on to the next step. So when we did the z-test, we needed to have the critical value. And you may recall for the z distribution, which is a fixed distribution that does not waver, when we set alpha at 0.05 for a non-directional test or a two-sided test, the critical z value was always plus minus 1.96. Well, the problem with the t distribution that we're now working with, as you may recall from the last lecture, is that the shape of it changes, it moves. So we would need a book to figure out the exact critical value, or at least a lot of sheets of paper, to figure out the exact critical value for our particular sample size that we're working with. So the nice thing with SPSS Output is we're going to get something even better. We don't need to have a critical value because SPSS will produce for us what is known as a probability value, a p-value. And that p-value, what it tells you is the exact probability of getting the t statistic that you got. And if we can tell by looking at that, it will tell us whether or not we have a rare t statistic or whether we have a common t statistic. So how do we find this thing called a p-value? Well, on SPSS Output, it calls the p-value either sig, S-I-G period, or in some cases, such as in this one where the arrow is pointing, sig two-tailed. So you'll hear me go back and forth, and you'll hear people talk about a sig value versus a probability value versus a p-value versus a significance value. All of those things mean the exact same thing. So sig two-tailed, significance value, p-value, probability value, they all mean the same thing. What you typically see in research reports is we just typically use the letter P to represent that. And that's what I want you to get used to doing. So in a few steps, we're going to see how we're going to be able to use that sig two-tailed value to make our final decision. So the critical value step, we're just going to pretty much overlook it going forward. I just want to introduce you to this concept on this slide. Let's move on to the next slide. So now in step 5 of our hypothesis test, we need to figure out the value of the observed t-statistic. Well, with the z that we did previously, you had to compute it, and I gave you a formula and you had to walk through it. Once again, for those of you who are a little bit scared of math, guess what? You don't have to compute anything anymore. All you have to do is find it, but we can find the observed t-statistic value on the SPSS output, but here's the tough thing. There are two values. we've got to figure out which one to choose. So let's look down at this test. So if you look at the red arrow, it points to a column that is labeled T. And below that, you see two values. You see a negative 1.191, and below it, you see a negative 1.166. So one of those is the correct T-statistic. One of them is a faker or a fraud or just not the right one, whatever. We need to figure out which one of those do we use. You'll notice that the negative 1.191, the top T value, if you go over to the left, the row it's in, it says equal variance is assumed. If you look down at the bottom T value, the negative 1.166, and it falls in the row called equal variance is not assumed. That is going to be our key point, the thing we have to figure out. And this brings us back to that thing that I introduced before called the Levines test. So that's where we're going to have to check that and interpret the findings of the Levines test to figure out which one to use. And the way that I often think about this is if you're a fan of poetry, Robert Frost wrote the poem, you know, two roads diverge in a yellow wood, and sorry I cannot travel both and be one traveler, yada, yada. You're at that. You're at a fork in the road. You need to figure out which road am I going to go down. Do I go down equal variances assumed, or do I go down equal variances not assumed? Because that will make all the difference, kind of in the end of the Robert Frost poem. Or if you don't like that analogy, think of Wizard of Oz. When Dorothy and Toto came to the Scarecrow and there was a fork in the yellow brick road and they had to figure out, do I go left, do I go right, right? That's where we're at. We're at the fork in the road. We need to properly interpret the Levines test in order to know which direction we take. So let's figure out how to do that. Let's move on to the next slide. All right, so let's take a closer look at the Levines test. What does it do? Well, the Levines test checks the assumption of homogeneity of variances, and it provides us with two pieces of information on any time we look at it on output. One, it gives us the Levines statistic. The Levines statistic is measured with an F. And we'll be talking more about F statistics in later lectures. But you'll notice under the Levines test for equality of variances, you'll see there's an F column and then it has a value, 2.720. Well, unless you are really adept with statistics, you don't know what to do with that. For us, the more important thing is the second thing that's provided with the Levines test, and that is, once again, that thing called a p-value, the probability or significance value for that particular Levines statistic. So you'll see that there's also under the Levines test, there is a sig. It has its own sig. It tells you how rare is the F. And that's what a p-value is. It tells you the probability of getting that F statistic of 2.720 or one even rarer. That's kind of the story behind a significance value or a p-value. All right, all that aside, let's look at what it is. Our main focus is a look at that p-value or sig value of 0.106. That 0.106 will tell us everything we need to know about, do I go equal variances assumed, or do I go equal variances not assumed? So I'll say that one more time. That value of 0.106, that is your map to tell you, can I go equal variances assumed, or do I have to go equal variances not assumed? So let's look at the next slide to figure out how we do that. Next slide. All right, so here on this slide, I'd give you sort of the way to read that map of that 0.106. So when you look at the Levines test, if your p-value is greater than 0.05, you can assume equal variances. But if your p-value is less than 0.05, you cannot assume equal variances. So p-value, once again, it's just another name for sig. So we look at that sig. Our sig is 0.106. So since that 0.106 is greater than 0.05, we can assume equal variances. And you'll notice what I've done here is I've circled that equal variance is assumed row of information, because once I have made my decision at the Levines test, I know which row of information is true and valid on my output. So all that bottom row of information, the equal variance is not assumed numbers, those are worthless to me. I want to put a line through them. I want to ignore them, whatever it takes. I want to highlight or focus only on the equal variances assumed information now that I've checked my Levines test. And my Levines test told me which way to go, left or right, the road untaken or the road less traveled, whatever. Okay, so now that we know we're focusing only on being able to assume equal variances, let's continue on with our test. Next slide. So our observed value of the t-statistic, as I said before, you don't have to compute it, you just got to find it. So since we can assume equal variances, we're going to use the output from the equal variances assumed row. So our t-statistic, we just pick the one that matches that. So our our observed t-statistic, is going to be negative 1.191. But there's one other thing that we are going to introduce here. Since we are working with a test that relies solely on sample data, in order to inform the public or to inform other researchers about the size of our sample and the nature of what we're working with, we should always report, along with our t, we should also report something else called the degrees of freedom. The degrees of freedom is abbreviated with a DF. Sometimes it's capital DF, sometimes it's lowercase. It's always a degrees of freedom. And that tells us a little bit about the sample size. You may recall from the previous lecture, I said for an independent samples t-test, the way that we compute the degrees of freedom is we take the sample size of group 1 plus the sample size of group 2, and then we subtract the constant 2. So the key thing that I want you to know right now is remind you that the degrees of freedom is very, very closely tied to the sample size. So it tells us about, are we working with a very large sample, or are we working with a smaller sample? And you may also recall that the sample size is important because it connects with power, right? So all these things start to come together as we continue on in this course. So you'll notice that the degrees of freedom, whether you remember the formula or not, doesn't really matter because, once again, SPSS gives it to you. So you'll notice that it says the degrees of freedom for the equal variances assumed is 48. All right, so we just need to know that. So we want to be able to, and the way we would say this is the value of our observed test statistic is the t, is negative 1.191, and the associated degrees of freedom is 48. So we have those two pieces of information for step 5. Now we can use that. Let's move on and figure out how we finally make our final test decision. Let's move on to the next slide. Okay, we're almost home. We're at step 6 at the test decision. Remember, our test decision, we have to make one of two choices. We are either going to reject the null hypothesis and conclude that there is a significant difference in maximum bench press weights, or we're going to say, we don't have enough information to conclude that there's a significant difference, and we fail to reject the null hypothesis. Well, for the z-test that we did previously, we just compared our observed test statistic to the critical value to see whether or not we fell in the common or rare areas of the distribution. For this, now since we didn't have a critical value, we need to figure out, where can I look? Well, on the output, there are two places that we can look. The first is to look at the p-value for the observed t-statistic. And as you'll notice in the blue writing that I have on this slide, that is referred to as sig two-tailed on the output. Why does it say sig two-tailed? Well, it's two-tailed because we're doing a two-tailed test, a non-directional test. So that sig two-tailed is the p-value for the t-statistic. We can also look at the 95% confidence interval of the difference. So the sort of the golden choice here is what we see in blue, is to look at the sig two-tailed, the p-value. So we're going to look at that. You'll notice that since we're only working with equal variances assumed, our p-value for the t-statistic is 0.240. And we're going to talk about on the next slide how we interpret that. We also look at the 95% confidence interval of the difference. And this is just like the confidence interval we did before with a sample mean, but now we're looking at the confidence interval for the difference between two sample means, right? So all these things sort of build on each other. And you'll notice there's a lower bound and an upper bound for that 95% confidence interval. We have a lower bound of negative 53.95747, and we have an upper bound of positive 13.8221. All right, let's take a look at how we can interpret both of those to make our decision. Next slide. So we'll start with what I said was sort of the golden choice, and what we see here in blue. That is sort of our go-to. P-values are something I want to make sure you understand before the end of this semester. So we know that the p-value for the observed t-statistic is 0.240. Well, how do I interpret that? Well, in the black right below there, you'll see that if p is less than 0.05 versus if p is greater than 0.05. That is something you want to make sure, if you learn nothing else this semester, this may be one of the most important things I want you to take away. So if your p-value is less than 0.05, you can reject the null hypothesis. So once again, if your p-value is less than 0.05, you can reject the null hypothesis. Why is that? Well, if your p-value is less than 0.05, it's saying that your observed t-statistic is so rare that it's out in those far rare corners of the distribution, and therefore you can reject the null hypothesis. On the other hand, if your p-value is greater than 0.05, that means your t-value falls into the common area and you cannot reject the null hypothesis, or you fail to reject the null hypothesis. So looking at ours, our value is 0.240. That is greater than 0.05, so unfortunately for this test, we're going to fail to reject the null hypothesis. The backup that we can double check that we're going to do everything is we need to look at the confidence interval. So if we look at the confidence interval, you'll notice it starts at negative 53.95747, and then it runs up to 13.82221. Remember, a confidence interval provides us with a range of values that is likely to include the unknown population value. And in this case, the unknown population value that we're trying to figure out is the difference between these two prison gangs. Well, the null hypothesis said that they were equal, right? That the mean for the innocents was equal to the mean for the meatheads. Well, if they're equal, that's saying that the difference is 0. So when we look at the confidence interval, if 0 is a possibility within that range of values, we cannot reject the null hypothesis. So by looking at it, well, thinking about a number line, it starts at a negative 53.95, and then it goes up to a positive 13.82. Well, on a number line, 0 falls between negative 53.95747 and positive 13.82221. So 0 is possible in this case, and so that also confirms our decision that we fail to reject the null hypothesis. So both the p-value and the confidence interval will give you the exact same answer. They never contradict each other. So it's a good way to double check your findings is by looking at these two. So it appears that in this particular hypothesis test, our decision is going to be to fail to reject the null hypothesis. So let's go on to one last slide just to take a look at how we might sort of summarize or conclude our findings. Next slide. All right, so as we mentioned on the previous slide, we failed to reject the null hypothesis. So before I go into stuff that's all in the fancy coloring and the arrows, whatever, let's look at the little quoted statement down at the bottom. If I was writing this up for a research report or a journal article or something on those, I might say something along the lines of this. And you'll notice how I can sort of summarize everything in one short sentence without having to have my readers go through all 6 steps of my hypothesis test. So I could say, based upon the results of an independent samples t-test, there is not enough evidence to conclude that there is a significant difference in strength levels between the two rival prison gangs. And then you'll notice at the end of that sentence, I've got a bunch of numbers thrown in there. This is a way for us as statisticians to be able to convey our findings in a nice, concise manner to the general public who may not have as much knowledge about statistics as we have. So all those numbers at the end tell somebody who knows what they're looking for a lot of good information. You'll notice the blue, first we say, okay, it's a T. That's the type of test we're working on. If we were doing an F test, we would put an F. If we were doing chi-square, we would do the chi-square symbol and things of that nature. So we tell them that the statistic we were working with, a t, then in sort of parentheses right next to it, you'll notice that we have the number 48. That 48 was the degrees of freedom. And as I said before, we often like to report that along with our t statistic because it allows other researchers to understand a little bit about the sample size we were working with, whether it was really small, really large, or somewhere in between. So we report that sort of in subscript next to the statistic that we're using. Then in green, we give the actual value of the t statistic we observed, which was at negative 1.191. And then we finish off by telling them the p-value for the particular statistic. And that's where we see sort of in that orangish brown color, the p equals 0.240. So right there in one nice little tightly wrapped package, we've told them 4 things: the type of test we're doing, the degrees of freedom, the observed value for that test, as well as the significance of that test. And it allows us to have everything sort of nicely wrapped up without having to go sentence after sentence and walk through the entire test. Okay, that concludes our first hypothesis test example for the independent samples t-test. The next couple slides are going to be 2 more examples that you can kind of walk through on your own. You'll see an SPSS output, and then you'll see a slide that looks like this that sort of has a conclusion wrapping up what we're finding. So let's walk through the next one. I'll walk through with you. And the final one, I'll kind of keep quiet, but you can look through it and practice with it as you like. So let's move on to the next slide. All right, so in this example, what we have here is, once again, it's a t-test. This one says results from the independent samples t-test assessing differences in minutes of exercise each day between individuals with personal trainers versus those without personal trainers. So let's make sure that this fits the requirements of an independent samples t-test. Let's look at our variables. You'll notice, looking at the group statistics box, as I said before, the first thing we see at the far left is our dependent variable, minutes of exercise each day. And I think you can probably understand that that fits the requirement of being a continuous quantitative variable, minutes of exercise each day. Then we have the trainer type. That is our independent variable. And once again, it fits the t-test because it's broken into 2 groups. Either you have no trainer or you have a trainer, so no trainer with trainer. Then we have the sample sizes, then we have the means. And in that group statistics box, we're not going to be worried about the standard deviation or standard error of the mean for this class. We will pretty much just care about the first, couple columns there. All right, then down in the independent samples box, once again, we go through it step by step. We have to start with looking at that Levines test, right? Remember, this is that fork in the road. Can I assume equal variances or do I not assume equal variances? So I see an F value for the Levines test of 5.278, but I don't really know how to interpret that. I need the p value associated with that statistic in order to figure out whether or not I can assume equal variances or whether I cannot. So I look at that sig of 0.027, and that's going to tell me whether or not I can assume equal variances. And you may recall, for the Levines test, if the p-value is greater than 0.05, I can assume equal variances. If the p-value is less than 0.05, I cannot assume equal variances. So in this particular example, my sig, my p-value is 0.027. That is less than 0.05, so I cannot assume equal variances. So different from our previous example, in this one, I am going to be, from here on out, only interpreting information from the bottom row. The equal variance is not assumed. So my t will be that negative 3.030. The degrees of freedom will be that 38.305. The sig, or the p-value for the t, will be that 0.004, etc. So we move on to the next slide. And here we would have our conclusion for our second hypothesis test. where we would reject the null hypothesis. And once again, you notice I've sort of presented it in a similar way, and I rejected the null hypothesis for this one. Why? Because the sig was less than 0.05, and I also could have confirmed it by looking at the confidence interval. And if you look at the confidence interval on the previous slide, you'll notice that it does not include the possibility of 0. And then you can see an interpretation of how we might do that in the black quote down at the very bottom. Next slide. This is our final hypothesis testing example. This one is looking at whether or not there is a significant difference in the number of fan-related fights at baseball versus football games, so at two different types of sporting events. So for this one, I'm not going to say anything else. The one thing I will mention before I just go silent and say goodbye for this lecture is pay close attention to the sig2 tailed in the independent samples test box. You'll notice one is 0.049 and the other is 0.055. This is a reminder of why it is so important to appropriately recognize and interpret the Levines test, because in this particular situation, if you go down the wrong road, you would come to a false conclusion at the end of your hypothesis test. And it's really close, but it does make a difference. All right, I will sign off there, and I will see you with the next lecture.